of our recent work with you, and I'd love to hear your thoughts about it. So, um, let me see if can you see it in slideshow? Yes.
Yes.
Super, great. So today I'm going to talk about guessing random additive noise decoding, which, as Arpan said, is a decoding algorithm. And I think one of the things that's interesting about this, particularly to the Signal Processing Society, and I'll mention some ongoing work also in the signal processing and grant domain towards the end of the talk, is that most of what I'm going to present today on the algorithmic side actually appeared in transactional signal processing, which is unusual for decoding algorithms, which are generally more associated with the process, with the transactions for which I am, as Arpan said, currently editor-in-chief, the IEEE Transactions on Information Theory. Now, all the algorithmic work and mathematical work today is with Ken Duffy, and all of that work and all of the implementation work is also with him. All of the circuits work is with our colleague Rabia Digital. So Ken was formerly at Maynooth University, where he headed the Hamilton Institute in Ireland. He has now moved to Northeastern University here in Boston. So we have a nice little Boston-based group of collaborators. So what is guessing random additive noise, and why are we looking today at decoding? So very often when people talk about the correction of errors, they don't really talk about decoding. They really just talk about coding. People say, "Oh, coding theory, or coding," and let's look a little bit at what error correction coding is, which again, most people might not associate immediately with the Signal Processing Society, or that end of electrical engineering. Okay, so why do we code? So suppose that I have a string of bits. So here you see on the left-hand side, I have 8 bits. And one of the bits gets flipped. It gets flipped maybe because I did some storage and there was a mistake either in the storage or in reading it back out, or it gets flipped because I was transmitting it and there was some noise in the environment. That's, of course, what we're going to be concentrating on today. And that noise in the environment also flipped the last bit. Now, in the first case, in storage, we in the environment where we have no soft information. That's to say, we don't really have a signal to interpret. We just have a 0 or 1. That's called a hard detection. There's a hard decision with no notion of reliability. In the second case, we have soft detection. So I've shown here different colors to indicate that maybe some there was more noise in some than others, or more expected noise. And that's the case of soft detection, in which case you have this extra reliability information, again, very much related to the signal processing aspects that we're going to cover today. And when you have that soft detection, you have some extra information, which might help you, which might help guide you towards thinking that the last bit is the most unreliable bit. That's the one that had, the most noise. Okay. So, in order to try to make up for those errors, like I showed you before, we had 8 bits. I need to add what we often call redundancy. I don't really like the name redundancy because it makes it sound like it's superfluous in some way. I prefer the name repair, because they're not redundant bits. They needed bits. They needed for repair. And what Shannon looked at in 1948 is to say, well, I would like to have a reliable transmission. I'd like to recover the original message, and I would like to add as little redundancy as possible. So how do I do that? Well, I send you a string of bits. The example I just showed you, they were n bits, where n was 8. I can't send you 2 to the 8 messages, because then, the message that you received, even though it was incorrect, might look like a correct message, and then there's no way to correct to go back to the original message. So we need to add some of these repair bits. And in order to do that, it means that I'm going to have to send code words, as I say, legitimate messages, which are fewer, sparser than the entire set, the entire 2 to the 8 possible bits. So maybe there are 2 to the k code words, so maybe 6, so maybe I only allowed 2 to the 6 possible code words. And the rate of my code in that case would be 4 over 8. So it would be basically, sorry, it would be 6 over 8. So it would be a 3/4 rate. So the highest rate that a codebook can have, that is called the capacity of a channel, and that's the highest rate that you can have, while still, given the statistics of the channel, so everything's always a statistical type of guarantee, statistically you can obtain the original message back. And that capacity is going to depend on the Shannon entropy of the noise effect, which is the effect that flipped in the example that I gave, that last bit. And I'm going to denote that by H, capital H. And the best correction performance, bang for the buck, these Shannon told us, comes at long code lengths. Now, of course, one of the questions is, how long do these code lengths have to be? Okay. Now, the original proof by Shannon did a construction of codes which was random, and the way he did it is he took the 2 to the k code words, took a bag of 2 to the n strings, grabbed the first code word, went into the bag of 2 to the n strings, matched the code word to the string of length n, so recorded that matching and kept doing that to the k times, created then a code book, which was this big dictionary to the k entries, gave it to the receiver, and then transmitted, and the receiver and the sender used that. Now, you don't need to do this assignment, this arbitrary random assignment. In practice, you can actually just use a linear matrix. So you can do an assignment by taking a string of length k, so 8 bits, a string of 6 bits, and then putting it through a 6 by 8 matrix, generate a matrix, and that gives you a code word. So that's actually what can be done. And it was shown in the late 60s, early 70s by Bob Gallagher that actually this linear assignment, if done randomly, has exactly the same desired properties as the random matching by going and dipping into a bag of length n strings that I just described. So the encoding and the codebook aspects actually are not difficult, can be described very, very succinctly. So the problem that we have is not really encoding, even though, as I mentioned before, we usually talk about coding theory. The problem that we have is not built-in codes. We can build random codes. We can build random linear codes that are succinctly described. The problem that we have is that the decoding is hard. And in particular, there's a result from Gleason van Tilburg in the 1970s that shows that optimal hard detection, so remember hard detection is just with the bits with no reliability information, is NP complete. Indeed, it is this NP completeness that lies behind some of the most perennially robust algorithms for post-quantum encryption, such as Gleason encryption, relies in many ways on this NP completeness. Okay, so the encoding is easy, the decoding is hard. So if you say, the decoding is hard, it sounds like it's just, that's it, forget about it. There's nothing to be done. However, the decoding is hard over a completely general case. That's to say, over arbitrary cases of noise. And in particular, remember that the whole premise of the setup of reliability and capacity relied on this Shannon entropy H. So let's go back. What we're going to do today is let's go back and look at this Shannon entropy H. So currently, because people haven't looked so much specifically at this center being revisited, the current paradigm is a co-design of restricted codes and decoder pairs. So for instance, you have CRC, cyclic redundancy.
Dr. Medard, can you hear me? Dr. Medard, your sound is not audible. Dr. Medard?
All of these different codes, CRCs, read mules, BCHs, et cetera, with one single approach of guessing random additive noise decoding. All right, so let's see how we're going to do that. So remember that I had, in the example before, if I had a length 8 a bit transmission, but I really had length 6 bit messages, that means that the number of messages, which we call X, even though they're of length 8 bits, there was only 2 to the 6 of them. Okay, so that's 2 to the NR because R is 3/4. And the number of bits that would be required actually to describe the noise, if we were only interested in describing the noise, will correspond to the cardinality of the likely noise sequences. And of course, the noise sequences themselves have length n. Any bit might be affected by noise, where we're going to look at noise as an additive process. So for instance, if I'm in a binary setting, having noise is the addition of a 1 modulo 2. So if I had a 0 and have noise, it flips it to a 1, or it flips it, or if I had a 1 and it has noise, it flips it to a 0. So of course, the noise could happen anywhere in these n bits, but the likely set of noises actually has a much smaller cardinality. So the noise is very sparse from a probabilistic point of view, and I can describe with high probability the cardinality, that possibility of noises, as 2 to the nh. And that's the amount of redundancy that I would need. Clearly, in order to be able to, from Y, the received signal, recover X, it means that I'm also able to recover the noise, because we have a system which is additive, or in general invertible, and therefore that means that I can invert the effect of the noise into the out of the Y in order to recover the X. Okay, so that's the redundancy that I would need, is basically enough to describe that to the NH. Okay. So the standard decoder would try to actually identify the X using the structure of the codebook. Okay, so what it would do is it would look at the Y, and it would try to identify out of, in effect, this dictionary, which X looked in some sense through a variety of different distance metrics the most like the Y. What we're going to do is actually we're not going to look at the X, and the reason we're not looking at the X is, remember, we want the R to be large. And in general, the code word is not going to be of length 8, like the example that I just gave, because it had to be short and fit on the slide. As you recall that I mentioned, it has to be, somewhat longer. We don't really need it to be, massively long, but not 8. So, let's look at, say, 100. So already, if I have a rate, say, 3/4, and I have a length 100, that's already getting too long for me to do a full search, exhaustive search. Okay, so I'm going to look at the noise. And why do I look at the noise? So what is, let's say, the typical bit flip in a channel? It's going to be 2 to the nh. So 2 to the nh, where h is, say, 10 to the minus 3, 10 to the minus 4. Even if it's 10 to the minus 2, if n is of length, say, 100, 200, and h is 10 to the minus 3, because the entropy is roughly of the order of the probability of a bit flip, now what I have is I really have 2 to the 1. So the number of bit flips that are likely is actually very, very small. The cardinality of that set is very small. And what we're going to do is we're going to do in Grant is we're going to be completely noise centric. So I'm going to try to identify the N using the structure of the noise. I'm so sorry. I have. Pardon?
The internet's working.
It is working. Yeah. Can you hear me?
Yes, can hear you. Yes.
Yes, it's working. Thank you. No problem. No problem. Actually, the co-author, Professor Duffy, who is also my husband, was having internet problems, and he thought that maybe I was talking into a hole, but it's good to know I'm not. So we're going to have two aspects, which are the codebook membership test, so to check that a codebook is correct, and the why. So now I don't really care about this generator of the code word, and in terms of how cleverly it is done. All I really care about is just to use it as a hash, as a check of whether something is in the code book or not. And this is what we're going to do. We're going to look at noise effects from most likely noise effect, generally no noise at all, to most likely. And we're going to do that in a way which basically goes through these effects until we hit a code word. Okay, and then when we hit a code word, we're going to return it, and that's actually going to be the most likely code word. So this is a maximum likelihood detector. Basically, think of it as a maximum likelihood detector. It's also a maximum a posteriori probability detector, because the probability of the original code words, it's all uniform. Okay, so this approach that I just described is universal, and it's suitable for any moderate redundancy. So that's the n minus k. So it's not really about the rate. It's not really about the n. It's about the number of repair bits, n minus k. The complexity is not a function of the structure of the code, which is very different from traditional decoding. It's actually a function of the statistical realizations of the noise, and it's highly parallelizable, and as we'll see, that makes it quite suitable for hardware. Okay, so why is this maximum likelihood? Well, the channel output is the input plus the noise. We're quite used to that. We all do signal processing. And the maximum likelihood decoding is the argmax of the possible code words in the codebook, which I'm denoting here by cal C, so of length n. It's the argmax of the code word that maximizes the a posteriori probability. Okay, now it turns out, because of course we have here an additive system, that it's the same thing for me to choose the argmax of the CN as it is for me to choose the most likely noise. Okay, and that's to say this is the same thing as the C that maximizes the probability of the noise. Now we don't usually think of the C as maximize the probability of the noise, but the two are perfectly equivalent. And then for the ML decoding, the maximum likelihood decoding by sequential guessing, makes sure that I'm always picking the noise effect, which will have maximized that probability of the noise, and therefore gives me the most likely the C star as a consequence. Okay, so if we do this, we automatically get capacity results. It's actually interesting if any of you do teaching. I no longer teach decoding and the coding theorem in the traditional way, which I had for years. I use GRAND. It saves me a huge amount of time in teaching, but also I should say the students relate to it and respond to it very well. And I know some of my other colleagues have started teaching that way. Okay, so what kind of codes can I have? Well, remember, I have a mapping from a string of length k to a string of length n. And because there are 2 to the k possible code words, 2 to the k minus 1 are possibly erroneous, right? There's that many mistakes. So how many possible guesses do I need to do? So let's do a very simple counting argument. If the code book was chosen at random, which remember that's what Shannon had told us would actually get us to capacity, the likelihood that a codebook query identifies a code word just by choosing, just because the codebook was chosen at random, and just to remind people of what the argument was with Shannon, is that the codebook, of course, was chosen at random prior to the transmission, but you do the analysis as though it was chosen at random post the transmission. Okay, just keep that in mind. So the probability the codebook query identifies a code word is approximately the ratio of the number of total bits to the number of total code words. So it'll be to the minus n plus k. And therefore, the number of queries, if I was just to use a uniform querying, would be geometric until I hit a code word, would be geometrically distributed with that probability. So the average number of queries until I find an incorrect decoding is going to go as basically 2 to the n minus k. So it doesn't really depend on n. It doesn't really depend on k. It just depends on the difference. So I could have a long codebook with a small number of redundancy bits, or I could have a short codebook with a small number of moderate number. It doesn't really have to be that small. We'll see that later. And that's really all I need. So any GRAND algorithm will find an erroneous decoding after approximately to the n minus k codebook queries. And actually, if you plot this, empirically, you can plot this for CRCs, for PACs, which are polarization-assisted convolutional codes, for random linear codes. You see that it actually fit this geometric approximation very well, and the decoding is really not influenced by the code book much at all. Okay. Okay, you can do theorems, but that's not what we're going to do today. So just to give you a small idea of how well this does, these are some established information theoretic bounds for how well you can do for different lengths. So here what you see is a probability of a bit flip of 10 to the minus 2. My target Blair, which stands for block error rate. So the block is a code word. So it's the probability of a code word being wrong here is also 10 to the minus 2. So if I have suppose I have a code word of length 100, and I didn't code at all because my probability of a bit flip is 10 to the minus 2. My code length was 100. Then the probability that I have an error there would be roughly 1, right, by a simple union bound. So by coding, I'm basically bringing the block error rate over those 100 bits back to the original per bit block error rate of 10 to the minus 2. And that's always a pretty good rule of thumb, I would say, in many channels, that you're coding to bring the block error rate back to the original bit error rate. Okay, so what I have here is the capacity. You can see the capacity is about 0.9. you see, and of course, that is the most that you can even get, even with an absolutely um, um, infinite length code book. You have a converse, which is shown there in red, which I'm not going to go into. A couple of achievability results. These are not constructive achievability results, by the way. These are just theoretical achievability results, ontological results, if you will. Most codes don't get there. And what you can see is that by using a random linear code, and this is not a particularly well-chosen random linear code, it's really chosen at random with just, out of just a couple of small little checks, such as the fact that, the code is not all zeros and the such. By the way, the bounds, not our results in purple, but the bounds are found in a GitHub, which is of bounds curated by my colleague, Yuri Polyansky at MIT. So he has a bunch of these bounds, which he keeps there, very useful. And what you can see here is now with a random linear code, I can do any rate, any length, because of course I can create my generate a matrix G randomly, of any size, and any rate, any amount of redundancy, however I want. So these would be, for instance, codes that would be known in theory, but up until now had not been decoded in practice. Okay, so back to the decoding. Now, this is the Signal Processing Society. We spent the first half of our time together here talking about decoding, because otherwise the rest won't make sense. But it's the soft detection that's probably most interesting and most related to the issues of signal processing. And what do we mean by the soft detection? Here I show you in the IQ domain, so real, so in phase and quadrature and imaginary. I'm showing you a signal here. It's a 4 PSK, and you can see in this signal the likelihood ratio of where warmer means that I'm a higher likelihood ratio, cooler means that I have lower likelihood ratio. And you can see that the areas near the boundary of the decision between 2 points is cooler. Of course, I have less reliability. And as I move away from the other possible candidate points, I have warmer colors. I have higher likelihood ratio. So this reliability or confidence is going from low to high. And so I am demodulating bits because I need to be able to manage them in a digital domain, but I'm not just demodulating the bits like I did with hard detection. I'm also keeping the soft information, this reliability. And what will happen is we will be quantizing the soft information. Most chips quantize it to between 3 and 5 bits. So we're looking at between 3 and 5 bits of quantization information of the soft detection per bit, not quite of information because they're coded, but per bit from the code book. Okay, so let's go back to our original guessing random additive noise decoder. How are we going to identify the noise? If the noise is continuous, of course, this approach to guessing the noise successively is not going to work in a naive fashion by just trying to identify the noise itself. But recall, we don't actually care about the noise itself. We actually care about X. So what we're going to do is not really care about the noise. We're caring about the effect of the noise. And you can see here is that even though the noise is continuous, the effect of the noise is still discrete. You can still only take one point to another point. There is no transmission of something which is not in this modulation. And therefore, there are different ways of doing this quantization to look at the noise effect. I'll mention a few here, but we're going to concentrate on the third one, the one in bold. So one of the things you could do is you can quantize down to 1 bit of symbol reliability. You could just say some bits are reliable. I'm not going to flip them. Some bits are not reliable. I'm going to flip them. That's called what we call signal reliability. Symbol reliability grant, and that of course reduces the complexity even further because you're in effect masking bits. You can actually look at the full reliabilities. That's soft grant, real value soft information, and that will give you the absolute maximum likelihood. But even though it's manageable, it actually has a data structure which is manageable. It's not very applicable for implementation in hardware. So we're not gonna look at that. We have DS Grant, which is M symbol reliability, which I'll mention at the end, but I'm not going to present any results. Which is what happens when you basically take the reliability information I showed you before, quantize it down to m bits, and after quantizing it down to m bits, you run something like the soft grant, which would be with the real value soft information. But I'm going to show you today something a little bit different, which appeared just last year in the transactional signal processing. It's ordered reliability bit grant, which is going to use log to n bit soft information, but actually I'm not going to use the full that full amount, as you'll see later. And one of the things that's interesting here is that I think it's maybe a somewhat different approach to signal processing, particularly statistical signal processing, than the one we take. Okay, so let's look at org grant. So we talked about log likelihood ratios. Again, to signal processing community, this is a very well known quantity and one that you're used to working with routinely. If I send you 500 bits and you just record, never mind, no code, nothing, it doesn't matter. Maybe it's coded, it's not, it doesn't matter. This is at the detection level. You just decode the absolute value of the log likelihood, and you just plot it. Okay, so you can see the log likelihoods here are ranging from close to 0 all the way to, almost 3.5. So a very wide spread of log likelihoods. This is a binary phase shift keying, so +1, -1, being sent in an added wide Gaussian noise channel. And then what I'm going to do is we're going to sort the bits. We're going to sort them from the most unreliable, so with the reliability at 0, close to 0, all the way to the most reliable. And you see these are multiple basically sample paths of that sorting, and each of these sample paths is denoted by a different color curve, and each of these sample paths is going to end up with a shape that's very similar to the others. Now, the most reliable bits, the ones that are towards the 500, those are probably not my problem. The action in terms of noise effect is happening towards the left-hand side of the figure with the not so reliable bits, not necessarily only the most unreliable, but the not so reliable. And you can see here that you have a very good approximation for the bits of interest of a linear model. It's a linear model for this absolute value of the log likelihood ratio. Okay, so in that case, if we have a linear model, what is it that's happening? So let me look at the probability that my noise is an actual particular vector. Let's call it Z. Okay, remember everything is of length n. Then the noises are independent, mutually independent, independent, identically distributed. But after I have seen the Y, I now have that they are independent still, but they're not identically distributed. The distribution of each noise effect is actually described by the log likelihood ratio for the particular Y symbol that I've observed, right? So now I have an a posteriori observation, which gives me an a posteriori probability for each particular noise realization. So if these log likelihood ratios, when ordered from least reliable to most reliable, remember have this linear shape, that means that basically I'm going to have a shape where the reliability is going to be roughly proportional with some constant proportionality that we denote here by beta, to I, which is the position in the reliability. Okay, so that's basically this picture here. I'm ordering from least reliable to more reliable, and the log likelihood ratio of reliability is proportional to the position along the abscissa. Okay. In that case, what happens to this sum, which is, this a posteriori probability, posteriori after the observation of y, of having had that particular noise effect? Well, the sum here in the exponent is going to be equal to the sum of these log likelihood ratios, which itself is going to be beta times the sum of the zi being 0 if there was a flip, except for the different locations of the noise effect. And that's going to be a particular kind of weight. It's not the Hamming weight, which many of you may recall have seen in information theory, which is the total number of errors. It's not the total number of errors. It's a weighted version of the total number of errors, and a weighted version that makes sense given this, this observation and given this ordering. And this appeared in ICASP, work by Ken Duffy in 2021. So he named this the logistic weight, and, it's not a name that was there before, but it's a name that makes sense. Okay, let me just speed up here a little bit. So the logistic weight is different from the Hamming weight, just you can tell that right away, but the Hamming weight just looks the number of errors. Here you look at the number of errors again with this weighting of I. But it is a weight, and so it's going to lend itself to actually creating these different patterns of errors. And the way we're going to create these patterns of errors, which we create on the fly, and by the way, we don't need to create them all. We just create these as we go along until we find a code word. Okay, so it's also something where we don't need to create all of the possible error patterns. We create them on the fly and we stop as soon as we find a code word. That's to say, as soon as removing that pattern of errors from the received signal is going to yield an element of the codebook. So here's an example, for instance, where I go up to 4 and I have the residual, however much I'm allowing myself. And, you can start by putting them as a block at the end, and you just make them basically pop down. We call this landslide algorithm. Not going to go into it, but just to say that this building up of these possible residual errors, and then having the blocks, fall down one after the other in order to build the possible the in order most likely possible error effects can actually be done very easily in hardware, or very effectively in hardware. How well does this do? Well, if you compare this to the state-of-the-art 4-5G CRC-aided successive cancellation list decoding, usually chips have a list size of 8. They try not to have a list size that's very large because the complexity of those of the legacy system goes up exponentially with the list size. So here we're leaving a list size of 16, which is a very generous list size. So if you look at what happens here, you can see that this orb grant approach applied to a CA polar code is giving us quite a bit of gain. It's already giving us 1 dB of gain. Here you have the block error rate versus SNR per bit. So EB over N0 is energy per bit over N0, the power spectral density of the noise. EB takes into account two elements, the SNR per bit, but it also takes into account the energy that's transmitted per information bit. That's to say, the more redundancy there is, the higher the EB. So of course, an EB that goes to the right is cost us as an energy, both in terms of transmit SNR, so amplifier power, and also in terms of extra redundancy / extra repair bits. All right, how do different codes do? Remember that our decoding algorithm actually does not depend does not depend on the codebook structure. It just uses the codebook structure as a hash, as a check of belonging to the codebook. And what you see here is that we have a system where the codebook structure really doesn't matter that much. And in effect, all, things like PAC, which is the latest, greatest codes, it basically does the same as a well-chosen CRC, which has been around forever and is, very easy to generate and check. They were actually built for easy checking and easy generation. That was the whole point of existence. And random linear codes, do quite well. Now, the only codes, which is a bit ironic because they're capacity achieving, but capacity achieving in the infinite domain, in the infinite regime, doesn't mean that you're particularly good in any sort of more operationally desirable regime, are polo codes, which is probably the reason why people added CRCs to the polo codes. But you can see that it's not really the polo code, it's really more the CRC that's doing the trick here. So we have constructed this chip in hardware. So like I said, our paper with Ken Duffy and our student Wei-An appeared at the end of 2022, but the work was already underway with the group of Rabia Zicigil and her students, first Arslan Riaz being the first author. And so we presented this at ISSCC this year, or this spring, in San Francisco. And you can see here the chip and the setup for measuring. And this approach that I just mentioned to you is very, very effective. So even though we don't care about the code, we're not making use of any property of the code, we are, with respect to the chips that have been that have been fabricated for CA Polo codes, we're about 20 times more effective in terms of energy per bit. They're shown here in hollow symbols, the couple of chips that were created, synthesized based on our ORGRAND work by other groups. So the chips to the right are not fabricated, which is one of the reasons why they can go to such higher throughputs. It's actually very difficult in a fabricated chip to get to such high throughputs. But even then, we're able to do better. So one of the reasons I'm bringing this up is because even though those synthesized designs were also using ORGRAND, which is how they were able to get down in energy per bit, there's, I think, a real benefit, and this is something certainly from my own for this group of collaborators' own experience. What I've seen is that having really the co-design of the algorithms with the chips, rather than just writing down the algorithm, handing it over to people who make the chips, and not having a tight connection and a real collaboration between the two, is really leaving a lot of performance untapped. So by the way, frame error rate here is it's the same thing as block error rate, and you can see we can do different frame error rates, and we show 10 to minus 5, 10 to minus 7 to sort of match what was out there in the literature in terms of target frame error rate. Okay. We get also, in terms of the fabricated systems, the largest throughput of all of them, again, just because of the simplicity of ORGRAND, particularly when, as I said, we did it together. So for instance, one of the things that we did is we didn't go through and do a full ordering, that full ordering that I showed you from least reliable to most reliable. We just ordered as we went along, and doing this, gradual ordering as we went along actually meant that we never had to go through the full ordering, and it was much more effective, much cheaper. Okay. If you look at the grand decoding region, say here's a bit flip probability of 10 to minus 3 corresponding to 9.8 dB SNR for binary phase shift keying in Gaussian noise. You can see that we can do very long codes. And you can see that the number of codebook queries per bit, so the actual work is very, very low. Okay, so we're doing very, very little work. Okay. So I'm going to now go through some of the aspects here, but just of some of the security aspects. But I just want to mention that GRAND actually opens a lot of possibilities for breaking wiretap codes, which may be a type of coding that some of you may have heard of. It's maybe more specialist area, but they have been pushed to be to secure the physical layer, and it turns out that we can actually, with GRAND, really reduce the security of these codes. So I would say almost break them. In some cases, we definitely break them. But okay, so what is one of the things, and again that we do as communication engineers, is remember the discussion about the independence of the noise that I mentioned when we were looking at, these, when I mentioned the noise was IID. Well, the noise is often not IID. The signals are not, why would the signals magically decorrelate to whatever rate you're sampling at, right? Why on earth would they do that? Really what we do is we tend to create a system that has that IID noise. And why do we do that? That's, again, we're sort of reconsidering the whole aspect around the architecture of how noise works. Well, the reason we do that is we collect data as rows and we transmit as columns in order to pretend or look like the noise is decorrelated. And it's because traditional legacy decoders cannot manage correlated noise. They do very badly in some cases. Generally they do badly, and sometimes they really break under correlated noise. So we're basically making the noise look decorrelated to match, in effect, the limitations of legacy decoder systems. That's the reason, right? It's not for detection. It's not for any other reason. It's really because traditional code-based decoders that are not universal are not able to handle generally correlation. Now, what does information theory tell us? Remember, we went back to Shannon. Let's go back to the source. Let's go back to information theory. Do we actually prefer noise that's correlated or noise that's decorrelated? So let's look at a simple noise model. As a matter of fact, for a given covariance matrix of noise, we know that the highest entropy noise, we know from Burke's theorem, is going to be a Gauss Markov noise. It's going to be Gaussian. If I look at the differential of entropy, that's to say the continuous version of that Shannon entropy that I mentioned at the before for a block of length, then what I'm going to have is that the differential entropy is actually going to be lower as rho, that correlation factor, which is showing here. It's basically showing the correlation exponentially dying off from the center. So this, this heat map here, hot means high correlation. So of course, along the diagonal, you're fully correlated because you're just taking a sample with itself, and it's dying off, going towards cooler colors as you go away. So what you can see here is that basically the differential entropy would go down. Now remember, from how we described GRAND, even though it was in the hard detection domain, that the lower the entropy, in effect, the fewer guesses I had to do, right? That basically the more sparse my noise effect becomes as the entropy of the noise goes down. So this is a desirable effect. So why are we actually doing this interleaving, which is trying to make the noise look uncorrelated when correlation is helpful? And how helpful is it? Well, let's see here. If I take a CA polar code and I have a correlation, but I don't use OrbGrand, I use CRC aided successive cancellation list decoding, you can see that the correlation, as the correlation goes up, the performance is getting worse and worse. Okay, so this correlation, which theoretically should be good for us because it's reducing the entropy, when we look at a decoder such as a CRC-aided successive cancellation list decoding, is actually hurting us. That's why people are putting in these interleavers, right? They're trying to push the curve to the left because if they leave the correlation in, the system does worse. Okay, what we're going to use here is a notion of approximate independence, which is that we're going to look at the correlation not over the entire block, but we're just going to look at neighboring correlation, okay? And so we're going to look at just B symbols, just a little neighborhood to capture most of that correlation. So what we've done is we've gone from a differential entropy and effect, which was the formula that I showed you before, to the formula that I showed you in below, where rather than look at the correlation over all the N, I'm only looking over the B. So the effective entropy is a little bit higher, but it's still managing to capture that row effect that is core to the reduction of the entropy. Okay? And now we're going to treat these little blocks of B symbols, and the B is not going to be very large, as you'll see. We're going to take these little blocks of B symbols, and now we're going to look at the noises being independent over these little blocks of B symbols, but we're going to keep the correlation within these blocks of B symbols. And now, if we apply OrbGrand with this knowledge of the correlation, what do we see? So you have in dashed lines now CASCL. And now you see as the correlation goes up, actually our performance goes up dramatically. So rather than getting worse as it does with traditional decoders, it gets better, and it gets better by a lot. We're talking here, around 10, we're talking here multiple dB of benefit from the correlation. And of course, we have already quite a bit of benefit from just using OrbGrand versus using CASCL. Okay, so here's the approximate independence. You can see some more results. And just to give you an idea, one of the big goals of 5G, which hasn't been quite met, it's really being sort of, I think, kicked to 6G, is to have ultra reliable low latency. So low latency is by putting short codes. Ultra reliable, the way they propose to get to ultra reliability is by having low rate codes. So for instance, rate 1/2. What you can see here is that if you use OrbGrand AI, OrbGrand with approximate independence, then actually for the same block error rate goal target of 10 to the -3, you can get rates which are above 0.9 with, or around 0.9 with a very, without very high rows, without very high correlations versus rates of 1/2. So basically what's happening is about a half of the resources right now being transmitted are being wasted. Okay. And with that, I hope to encourage you to, I'm going to leave a couple minutes for questions. I want to encourage you, if you've found this interesting, to visit our webpage for this project, Grand Decoder at mit.edu. And I hope you found this interesting from the aspect of really looking at the signals. We've looked at the noise, we looked at the correlation of the noise, we looked at, how to interpret log likelihoods in a different way. And I hope you found this interesting. I look forward to your questions.
Thank you very much. So yes, if anyone have any questions, feel free to ask over here. There's one of the thought from Dr. Monica Agarwal. She
Mhm.
wanted to know that how do we ensure this algorithm will converge?
Yeah, so it converges. Let me go back. Oops, sorry. So let me just go back to that slide. It converges because because as I said, you will you will almost always hit. That's why we get such good block error. It's the correct thing, but you will always hit a code word, right? You may hit the wrong code word, but in that case, it was still you always have an error. It will still be the wrong thing. So it never keeps going forever. It can't. You're gonna hit something. So you don't need to worry about its convergence. This is not like a belief propagation. Okay, you will always hit something. So the worst that can happen to you is 2 to the n minus k, where n minus k is the redundancy. Does that make sense? Does that answer your question?
I think she disconnected probably, maybe because it took. Couldn't see her name on this. But as it is getting recorded, I'm pretty sure that
Okay,
her query will
yeah.
be
But it will
resolved
always,
later.
so it will always hit something. You may end up hitting another code word, but in any case, that was an unavoidable mistake. You're still doing the maximum. But this is, it's not like a belief propagation or turbo where you just go around, hoping and praying that eventually you'll converge. You don't do that. You're always getting more and more likely. You're always advancing. And so the convergence is not an issue. It's not like a turbo or belief propagation.
Okay, one more question I would like to ask from my side is currently I'm in Taiwan, and basically we are designing this RF transceivers using MMIC. So as you were talking about the throughput, that the algorithm you have implemented is helping in increasing the throughput.
That's
So
right.
if at all for the transceiver applications, we would like to implement certain protocols, because for 5G, we are using even for Wi-Fi, we are using different protocols. So how to ensure that this particular algorithm will be useful in such communication system? I mean, we can just go for it straight away, or do we need to verify it first, or how does it work?
So this does not affect the entire protocol, right? This is only looking at the so I think there's two parts to your question, if I understand correctly. So let me repeat the question and tell me if I'm correct. So, I have an entire protocol. How do I put this in my protocol stack? And then, next thing is what else remains to be done with respect to the entire protocol. So let's start with the first question, which is this currently what I've presented to you is only looking at the phi layer. It's just improving the effect of the phi layer. It doesn't need to affect the rest of the protocol, okay? Now, the second part, which is, might I be able to use this then to create other protocols which actively make use of the fact that now my phi layer is better? So that's definitely the case. Okay, so there's like two parts to it, if you will. This can just be replacement of decoding at the phi layer, but then there's a knock-on effect, which is we might be able to have overall more effective protocols because current protocols have inefficiencies because of the poor behavior of legacy decoders. Does that answer your question?
Yes, that's correct. Thank you very much.
Yes, thank you. But what I've presented right now is just the phi layer, but of course there are interesting things that could be done in the protocol.
Yes, absolutely. That's the reason I asked you this question.
Yeah, exactly. But right now what I've presented is just at the phi layer.
Yes. Okay, so anyone else having any questions that needs to be, okay, there is one question. Okay, how it compares with BP in terms of complexity and performance for LDPC?
Yes.
That's a question by Mayur Punekar.
Yes, thank you. So we haven't done this for LDPCs. Typically, so most LDPCs out there have very big N minus K. So it's interesting actually, because we're talking about capacity. People think that LDPCs are good because they're capacity achieving, and they are capacity achieving. But the LDPCs that are being used, for instance, in 5G, are rate 2/3, 1/3, when the actual rate, as I showed you before, should be 0.99. Okay, so they're very, very far from capacity achieving for the channels over which we're using them. It's funny, it's like if people say, oh, it's capacity achieving. Yes, but not for your channel. It's capacity achieving for a different channel. So it's, again, the very wasteful. So they have very high N minus K, most of them. So we haven't been looking at them for very high N minus K. We've been doing some things around some other constructions of codes, which I didn't get into, but which we have published on, if you want to get to high N minus K. Does that answer your question?
Let me unmute. Okay, yeah, he said yes, thanks.
But if you had a low end, if you had an an LDPC with a lowish N minus K, that it doesn't matter. The codes wouldn't matter. But that's not why most people are interested in using them. Again, I'll hope that will change, because again, we're wasting a lot of energy transmitting needless bits. So, any other? Yes.
There are no doubts at the moment, but I think later if they will have any, then I can redirect them to you
Absolutely,
later.
yeah, absolutely, absolutely, yeah. You know where to find me, and
Yes.
I'm easy to find.
Yes, absolutely. Okay. So for now, we don't have any doubt for now, but in case after going through the presentation again and someone comes up with any kind of doubt, Dr. Medard, as she told that she's reachable anytime, right? So I mean, you can mail her or something and then she will
That's
revert it to you.
right. That's right. That's right. Absolutely.
Right. So
Okay.
So just for the vote of thanks, I would like to invite Dr. Mayuresh Kulkarni, who is the branch counselor for IEEE Silver Oak. So Dr. Mayuresh Kulkarni, over to you, sir.
I'm audible, sir?
Yes, absolutely.
Yes.
Thank you so much, ma'am. As the branch counselor of Silver Oak University IEEE student and faculty advisor of SPS Silver Oak University IEEE student branch chapter, I would like to express my sincere gratitude to everyone who has made this event a grand success. Firstly, I would like to extend my heartfelt thanks to Dr. Muriel for her insightful session on guessing random additive noise decoding. Our expertise and knowledge in the field of signal processing have enlightened all of us. And I'm sure that her session will help us in our future endeavors.
Thank you very much. Thank you for the invitation and the great questions. Sorry. Yeah.
Just a minute, ma'am. Just a minute.
Sorry. I can't see your face, so I have to.
Just give me a minute. Just a minute.
Sorry. Yes.
Mayuresh, sir?
Yeah, I'm there. Just coming back. Yeah.
Okay, no problem.
So sorry for the glitch. On behalf of IEEE Signal Processing Society Gujarat Section Chapter, I'd like to offer a virtual memento as a token of gratitude to Dr. Medard for conducting an amazing session.
Oh, thank you. Thanks a lot. Very kind.
I would also like to thank the IEEE Signal Processing Society and the IEEE Signal Processing Society Gujarat Section Chapter for the constant support and guidance throughout the year. I would like to thank Dr. Chirag Pamwala, sir, Chair of IEEE SPS Business Section Chapter, and Dr. Satif Khara, sir, who is member at large at IEEE SPS Business Section Chapter, for the support and guidance. I would also like to thank the members of IEEE Silver Oak University Signal Processing Chapter and IEEE CKPCET College of Engineering Signal Processing Society Chapter for collaborating with IEEE SPS Gujarat Section Chapter to organize this amazing session. Finally, I would like to thank all the executive committee members of IEEE Gujarat Section to be present. Your presence and support have been instrumental in making this event a grand success. Once again, thank you all for your participation and support. As a spark has indulged in ourselves, let us collaborate to make a positive impact in the field of signal processing. Thank you very much.
Thank you all. Thanks for attending. Thanks for the
Thank you,
great
ma'am.
questions, and thanks for the invitation. Bye-bye.
Thank you very much. Dr. Medard, I would just like to introduce our chair and the vice chair of the Signal Processing Society Gujarat chapter. Our chair, Professor Chirag Pamwala, and vice chair, Dr. Meeta Pamwala. They are with us over here.
Lovely to meet you.
Same here, madam.
Thank you. Bye-bye, everyone.
Okay, so next time we are looking forward to invite you here in physical mode. You know, sometimes if we get time to
three-dimensional.
India.
Yeah, we can reinvent ourselves. We project ourselves onto 2 dimensions. We can
Please
Yes.
your availability to come in a physical mode. We will do all the arrangements at our end.
I'm sorry, I didn't hear you.
Yeah, please tell your availability to come in the physical mode. So when you have the best time to come to India.
Oh, I've been to India a few times. I've always enjoyed it tremendously. So thank you. Thank you very much.
Chair is saying that you can share your availability whenever you're free, and then we'll be more than happy to arrange your
That's
travel
very
and
kind.
everything, you know.
Very kind. Thank you very much. Thank you.
Okay, thank you.